So last time, okay, let's get started. So we will continue the minimum model, but before that, the correction from last time. So unitarity means that representation of Universal algebra is unitary if here is space does not have negative norm state. I think I should upload a lecture note. I think I made a lot of correction. Did I? Let me put the latest lecture note into the e-learning now. Let's see. Okay. So last time I told you really stupid thing. So which means this is equal to 0, and also I mentioned that the equality holds only if this psi is indeed is it null or empty state? Equal is null state or empty state, and of course the vacuum is always normalized by 1. Sorry. So last time I just wrote 0. This means 0 means empty state last time, but last time I just what I meant is empty state should be 0. Empty state means 0 times some states. So this is of course 0. It's a Hilbert space, so it's a vector space. 0 times something is 0, of course. But for vacuum, is always normalized by 1. Okay, so this is not 0. Okay, so the last time I have written 0 is equal to 0, but this is not true. It's not what I meant. What I meant is this one, that empty state or null state. That's a huge mistake I made. So remember, vacuum is always normalized this one. This is a very important fact. So last time, so here's the unitary region. So it's easy to see that this HRS curve is always exists curve is in the region C is less than or equal to C1. So therefore here and then, as you know, so if you cross this curve, the Katz term will change the sign. So therefore here since this region does not cross the sign, the curve, so always the Katz determinant has the same sign. So recall that the Katz determinant, I already forgot the determinant Mn is some number times H minus HRS and P n minus RS, and then N is a level. I think this is a Katz determinant I introduced last time. What was it? Yep. So therefore, yeah, unless you cross this curve of HRS, the sign wouldn't change. So therefore, here always sign the same. Now, as you can easily see, if you take so if you take H is big large enough, H is really large enough, whatever, one or whatever. If H is large, if you take large, which means this region, if you go to take large enough, then you can always, the fixed n, given the n, you can just take the sufficient large H, you can easily see. So this part is positive, and then this is always positive integer, so the cost determinant is always positive. Okay. And the question is, so the of course a determinant. So for instance, -1, -1. So determinant equal to 1. Okay, positive, but which means that it has the matrix has a negative norm states. This means so therefore you have to show that the it's really positive definite. So it wouldn't happen. That's whatever. This is determinant is positive, but it's negative definite, right? So it has a negative eigenvalue. You have to show the eigenvalue is positive, or at worst 0 if you have null states. Okay. So this can be used by using the simple representation Virasoro algebra. I mean, simple representation Virasoro algebra. Okay, let me write down. So at level n, so you just write down the state of length n. Yeah, length n alpha. So let's call it alpha, state alpha. So length n. So length of the Virasoro algebra is, you can just write down, for instance, L, so level 3, L minus 1 to the cube, vacuum is actually length, corresponds to length 3, L minus 3, okay, L minus 1, L minus 2 is length 2. So how many Virasoro generator acts on the vacuum? L minus 3 of vacuum corresponds to length 1. So that's length and alpha, and you can just show that the alpha and alpha, if you just look at the sufficient large H alpha, so you can just have some constant H and alpha, and 1 plus order 1 for H, and also you can take alpha, beta, H and alpha plus and beta divided by 2 minus 1. And so this is order. Yeah. Sorry. Okay, I should write down order. Listen. And if you take H is sufficient large, so you can see that this diagonal part, so recall that the Mn is just a matrix, whatever matrix, which is, alpha, alpha beta, beta alpha, whatever, beta, and so on at the level n. So you just multiply the inner product at each level, okay, at each level. And so from this behavior, one can show that the H to the n alpha is dominant than the H to this guy. Once you take H and sufficient large n. So therefore, diagonal part is dominant in the sufficient large H. Now, as you can see, H is of course conformal dimension, which is for unitary for unitarity, H has to be positive, and alpha is of course positive, length because length. So always the diagonal part is positive definite. So therefore, so you can show so this when C is greater than 1, the theory is always unitary. And as I mentioned last time, so once you cross this the curve of HRS, so you change the sign. You change the sign. So therefore, so if you change sign means so the negative norm state will show up. So therefore, you can always you have to be very careful to do the analysis. And also, so this region always has a negative norm. And then when only intersect, so you have a possibility to have a unitary theory. And I'm not going to go into detail. You can just take a look at the card in the original paper. And when C, so always like last time I introduced P and P prime. For co-prime states, we'll give you minimum model, finite many minimum model. Which has the finite many primary. And however, so when P prime, so after you do the careful analysis, when P prime P plus 1 is only unitary minimum model. Okay. So M stands for minimum model in this lecture. Okay. And so otherwise, you get the non-unitary. It has negative norm states in the theory. So therefore, it cannot be described the physical theory, but even non-unitary minimum model has a very interesting structure. Interesting structure. So that it's not a really boring theory. I mean, it's a lots of intricate structure. I mean, and also it's related to nowadays. Okay, so it's a bit different, but it's somehow encodes information about so-called BPS states in supersymmetric field theory in 4 dimensions. That's also the one instance people nowadays call BPS safety correspondence. Let me put the latest lecture on e-learning. Actually, I changed a lot. Let me in e-learning. Okay, now it's changed. Sorry, I made lots of correction in the lecture note. You can take a look at the e-learning, latest one. Okay, so we will talk about the minimum model more in detail in this lecture. It's very important. I mean, minimum model is exactly some model, and which is one of the most important quantum field theory. And most of the university do not teach this important model, even though it's important quantum mechanical field theory. So it's a good time to learn great in detail, the minimum model great in detail. Okay, so let's talk about the character of the minimum model. Oh, before then, okay. Let's talk about character of minimum model. Okay, as we recall, the character of H of tau is just partition function, just counting Hilbert space. L is the CH, this is really the module, and QL0 minus C over 24. So I just only focus on the holomorphic part, and this is of course the irreducible representation of Virasoro algebra. Specified by minimum model. So once you specify P and P prime, P primes, so you can have the relation between C and H, and you specify, and this is minus C over 24, and then you just sum over dH of n q to the so this is a character erasure representation of Virasoro algebra. Okay, with highest weight H. So as you recall, so you just have a highest weight state H, and you just apply, and so on. The creation operator, or whatever you call it, of the Virasoro algebra, and then if you once you encounter null state, you have to throw away. Okay, so that's how you obtain the irreducible representation with highest weight H. And then you just count the Hilbert space, and this is degeneracy. Of level n, and then H plus n is really the conformal dimension of descendant, which can be easily obtained by using commutation relation for Virasoro algebra. Everyone should be able to do without asking. And then, of course, so sometimes you hit the null states, so dH of n should be less than this partition of the partition of n, less than or equal. At first time, most of the case, dH is equal to Pn. dH is equal to Pn. But at some point, you will hit the null states, so you have to throw it. That's why you have it in the column. And of course, so you can start with vacuum. So this is so if you start when H is the vacuum, or maybe phi 1 1. Is it vacuum? I think so. Anyway, so I may be wrong. Let me check. Yes, I think I'm correct. Okay. Anyway, so if you start with vacuum, so vacuum. This is my notation for vacuum. So this character is often called vacuum character. Most important character, and since it contains the theory only contains one vacuum state, it should start with 1 plus 1 plus q to the whatever, q to the something, some q to the power. Anyway, so it's always like some 1 plus some number times q, plus some number times q square, and so on. So you have the just counting generating function. It can be understood as a generating function of the states, descendants from a vacuum states. So this 1 is really coming from 0 and 0. Okay. And then there is no degeneracy, so it's always a unique vacuum character. And then so of course, if you put the theory on a torus as a torus partition function, and you impose a periodic, which means so Ramon. So periodic should be in trace of, we already learned this one. So this can be written as the NH H bar, and the character of h of tau, character of h bar of tau bar. Okay, so you have the holomorphic anti-holomorphic decomposition, and this n is the multiplicity. So this is multiplicity of primary state of conformal dimension of h bar. So how many primary you have of the conformal dimension of h bar? Okay. So given a primary which has a conformal dimension h bar, you can have a descendant in both holomorphic and anti-holomorphic sector, and you just count all of the number of descendants. And of course, since it's put on a torus, so you should enjoy the PSR2Z action. So this the PSR2Z should act on the ZBP tau and tau bar. And as we know, so the of course the T transformation is just a shift tau goes to tau plus 1, and by definition, so you can just consider character of your module should behave as e to the 2 by I h minus c over 24 chi h from definition. So if you take here is of course e to the 2 by I tau, and if you shift plus 1, you just receive h minus c over 24 contribution. Therefore, from here, so the invariance of under T will imply that the NH h bar is 0 if h minus h bar is not the integer. So to get the multiplicity, non-trivial multiplicity, so h difference between h and h minus h bar should be integer, which means that you can easily see. Of course, I mean, if you assume here, of course, we assume C left central chair and right central chair is the same. So yeah, I think okay. So let's talk about the whole non-chiral theory. Sorry, I think I should use this notation. Anyway, sometimes I mean physicists can consider holomorphic sector and left hand or holomorphic and anti-holomorphic sector can be different CFT. Can have different CFT, can different conform theory. In fact, so I taught this course in 2018, and after that, actually, I considered the CFT with chiral CFT, left moving and right moving, holomorphic, anti-holomorphic, a different CFT. With my students at that time, it's an undergrad student and also master student at that time. And we found a really new conformal field theory by considering different CFT in holomorphic and anti-holomorphic sector. So yeah, so lots of things. I mean, so 2D CFT has been studied from 1984 very intensively by many people from many aspects. But still, there are lots of interesting phenomena one can find in 2D CFT. So this is a constraint, and also so you have how about S transformation? S transformation is just tau goes to -1 over tau. Therefore, chi h of minus 1 over tau is indeed can be written as just a SH prime chi H prime of tau of the H prime. So since we know that in minimal model you have a finite many primary states, so therefore S matrix is a really finite matrix of finite size. Okay. That's very important. That's why you can often solve the exact. I mean, you can solve the theory exact. Okay. So this is a finite size matrix. And so the invariant on the S should tell you should be equal to and so this you can easily check. So this character should, so this should be this should act on VPP tau bar as an invariance, and then so invariance on the tau will impose the constraints on multiplicity in the Hilbert space on the force. And then of course, this will be automatically satisfied. Okay, yeah, it's okay. So and then when n h bar is diagonal, so this h bar is sorry, and not bar. It's fine. So it's the same compound dimension. If it is same compound dimension, then you can have it's called diagonal type. Diagonal type. Yeah, the obvious reason. So the multiplicity matrix is just 1, 1, 1, 1, and so on. Or sometimes it's called type A. Type A means that the actually A. So we will learn later. So this modular invariant partition function in the some CFT called SU2 with the model can be classified by so-called admiter, the eddy classification, celebrate eddy classification. It's there's a one-to-one correspondence of Lie group and also the modular invariant partition function. And in fact, so with like 3 years ago, with my students, we found something beyond the eddy classification. So yeah, in the research. But anyway, so yeah, I will talk about this partition function more in detail. So. So from Katz's determinant, so let's determine this character. So the character can be obtained by just looking at where the null state sits in. So from Katz's determinant B, so you start with HRS. Okay. You start with HRS. Now let's consider. Okay, so character in minimal model. Okay, P prime, and then you just consider the character of so one module of HRS. So you just consider one module. So then, so we know the Katz's determinant will tell you that the exists null state or singular state at level RS. Okay. at the level Rs. Okay. So therefore, the conformal dimension of this singular state is of course HRS plus RS. So this is of conformal dimension. Conformal dimension is, and this is if you substitute the formula for HRS, one can show that the H is the minus RS. Okay. So this is indeed the same as the conformal dimension H minus RS. And furthermore, we know that there's a symmetry between phi RS and you can identify with phi H, sorry, I forgot, P minus R and P prime minus S. That we learned last time. So we can just identify RS and the P minus R and the P prime minus RS. So therefore, one can do the same trick. So you start with H, P minus R, and then P prime minus S, and minus plus P minus R, and P prime minus S. So you just replace R by P minus R and S by P prime minus S. So then R times S becomes this guy. So this is indeed, if you substitute the formula for highest weight, conformal dimension for primary in the minimal model, you can just find this is H times P to P minus R. Okay. So therefore, so if you start with the primary RS, you encounter the new states of the conformal dimension spaced by minus RS and also 2P minus RS. So this is Bernoulli module. So I start with Bernoulli module. It's not the L. Did I erase? I think I erased. So this is trace is given by LCH. Trace is really irreducible module. That is different from Bernoulli module over there. Okay? The Bernoulli module contains lots of null states, whereas this irreducible module you have to throw away all null states. Okay? So at this point you encounter a null state that will again. So as I mentioned last time, so given the null states, even if you act on the creation operator, always null. Okay, so therefore it produce the submodule, okay, submodule inside of a module. So it's an infinite dimension module contains the infinite dimension submodule, and so on. And so you have to throw away. And the same thing happens. You just have the minus, it has the repeated pattern contains some module, and this will give you 2p plus r s and so on. So it has a sum module specify these two integers and so on. It becomes repeatedly. I'm not going to write down everything. So therefore, okay, 4p minus rs and minus 2p minus rs and so on. So you just, so this is, I think, the work by Katz. I mean, he's a representation theorist. So therefore, chi hrs of tau is indeed can be written as follows. So we know that the character of a module, which is the delicate error function given this one, like this way. However, so this will create a one character for one module, but you have to throw away one by one. Okay, you have to throw away one module contribution one by one, which means that the 24 k is integer q h So when, let's see, let's take a look at the one by one. K equals 0, you will reduce this to this guy. And k equal to 1, you reproduce this guy. Okay. So that's why you have to have a minus. You have to get rid of it. Okay. However, this contains another submodule, so you have to get rid of this guy too. So therefore, minus times minus is plus 1. So therefore, so when k equal to minus 1, this corresponds to this guy. When k equal to k equal to 1, that corresponds to this guy. Okay, minus 1 times minus 1, you get a plus. Again, this submodule contains another submodule. Okay, so therefore you have to subtract this guy too. So then you go to a minus sign. Minus 1 to the cube is minus 1. So you get to this guy, and when k equal to minus 1, this corresponds to this guy. When k equal to 2, this corresponds to this guy. Okay, and repeatedly. The next guy will come here when I don't know what's the number of k. You have to do it by yourself, and so on. So then you just exhaust all possible positive integer. Not positive, also negative, all integer. And this is the character of the here's the module. And if you define the set function, so then this can be written as the if you are really, and this is not I mean, if you're ambitious, you can just check. Just give you an answer. So it's not so difficult actually. If you're diligent enough, and then nowadays you can use some mathematics and so on, it's easy to check actually. This if you're diligent enough. And then my student did it 3 years ago. And tau. So here when p prime is equal to sorry, I think I should mention this is p prime is equal to p plus 1. Yeah, so this is a unitary minimum model. Sorry. So you can just check. Yeah, this is a case where the set function is defined by. So this is general set function. It's more than the one I showed last time, or like 2 lectures ago. Sum of n is integer, q to the k is in the quadratic category. Okay, so and then yeah, so you can also so you can just from this expression one can read off how this S transformation acts sum over I think I didn't mention. So I think this analysis. Yeah. So here I assume I should mention here I assume already a unitary minimum model. So this one, it's unitary minimum model. And p minus 1 and then chi. SRS r prime and s prime and chi r prime minus s prime and tau. And this S matrix can be written in terms of some sign function. I'm not going to write down. I mean everything written in the election notes, some number and minus 1, some number and then sign function. Pi r prime over p. It's a simple function. And then it's easy to generalize this S matrix for non-unitary. I mean, even non-unitary is not case, it's not. So everything written in terms of some function. So for instance, when so I will going to talk about the p equal to 3 case in soon. So p equals 3 case, this runs for S runs for 1, 2, right? 1, 2. So it's a 2 by 2 matrix. S matrix is 2 by 2 matrix. So can be written by same sign function. So it's very simple. It's very simple. Okay. And then, so what I meant is a diagram. So one can consider the diagonal modular invariant partition function of diagonal of MP is indeed can be written chi s. So you just always identify Rs and R prime S prime is the same, and you just do the square and the sum of all the primary. So this is the diagonal part. And one can also have a non-diagonal part, which is more interesting one. So multiplicity. So this is all the identity matrix. So this multiple I already raised. Multiple matrix and is diagonal matrix. That's why you can have just simple structure. But we will see later there's even like a non-diagonal one can be modular invariant by analyzing S and T as. Okay, any questions so far?
Does this change hold for non-unitary?
It has the non-unitary theory, at least minimum model of modular S and T matrix. So this at this part is okay. At this part is okay. But here you have to be a bit careful for non-unitary part. But I'm not going. I mean, the result is no, but it's a bit complicated. I just focus on the unitary minimum model. Any other questions? Okay, so now we are going to talk about the most important to the CFT from now. As a model. Right. So as a model. In introduction, I talk about as a model for critical phenomena, and then when p equals to 3, one can just easily deduce how many primary states and you have, how many primary states you have, so that the I think I made a mistake, I guess. I think it's this one. Let me check. It's recorded, so let me check. I think I told you wrong. I think I made a convention wrong. Let me check now. Yeah, I'm wondering it should be P, I guess. That's my impression. Instead of P minus sound. Let me check. I may be wrong. I'm just wondering which one is correct. I think in the past I give you the homework to derive, because I mean it's 3 primary. Okay, let me. Okay, I would check this one. This may be just P. Sorry, this may be P. I will check during the break. This may be P. I think this is P minus, it should be P. I think I forgot which one is correct. So, yeah, it should be P. Sorry. It should be P, right? Because I mean, either model has 3 primaries, so. Okay, anyway, so I will correct it if I'm wrong. If I'm wrong, I will correct it during the break. Or you can just check whatever books you have at this moment and tell me which one is correct. So this is the R and S, whichever call it. So you have a 0, 1/2, 1/16, 1/16, 1/2, and 0. So this is a component dimension. That's a component dimension. HRS. And of course, C is specified by 1 minus 6p, p plus 1. I think I'm correct. And once you substitute p equal to 1, p equals 3, and this is equal to 1/2. Okay. Central charge is the same as the free Fermi. Okay. So we already see the relation to the Fermion, free Fermion, and then we call these, and we have again this symmetry of p minus r and p prime, p plus 1 minus s. So if you use this identification, you can just check that the sigma sigma epsilon epsilon. And by comparing component dimension, so as you know, so whatever primary EZ E0 2-point function is some number divided by Z 1/2 times. It should, yeah, 1/2, or more precisely, I mean, if you use the this is the case, and then sigma z bar and sigma 0, 0, 2-point function, it should be 1/8. Okay. So from here, so as I mentioned, this can be understood as a critical, this power. So this 1 can be understood as the critical exponent. So when the Ising model, Ising model, as I mentioned, so you consider the lattice, and you can just consider each side you have a spin, whatever call it, spin up and down. The Hamiltonian is given by minus j sum over the interaction of neighboring spin site, which is sigma I plus 1. Sigma I and sigma j, and I and j are neighboring sites. And then if you consider, so j is actually proportional to, no, sorry. And if you consider the partition function, we will see is equal to e to the sum of all state e to the minus k Boltzmann constant what e. Okay, so this is the partition function in statical mechanics, and when T approaches to Curie temperature, the theory becomes CFT. Okay. That's what I told you last time at the first lecture. And then, so at this Curie temperature, all the correlation function in the 2-point function of the energy density operator and then spin operator obeys this power law. Okay, power law in the exponent. Exponent. So this number is critical exponent. This is indeed in conformal theory. It's just a conformal dimension. Okay, 2 times conformal dimension. Okay. Oh. So what did I mention about the? So okay, I didn't print out lecture note. I think I'm pretty sure what I have written in introduction is correct. Yeah, it's okay. It's okay. I don't care about the yellow book. So it 1 and 1/8, right? No, it should be okay. It's a conformal dimension. So, and we will see more in detail. So the primary state, in fact, so therefore this energy density operator and the spin operator can be understood as the primary of this minimal model can be understood. And furthermore, we can just analyze this Ising model more in detail because it's the most important one. So if you write down, this is just Hamiltonian. Therefore, you can just write down this one is equal to all state e to the minus k sum over sigma I, sigma j, and I and j, where k is equal to j over kb Boltzmann weight, Boltzmann constant. Sorry. Okay. And then, so you recall that the e to the x, whatever, minus k sigma. So let's look at this guy. So this can be written as cosh of minus k 1 plus sigma I, sigma j, tanh of minus k. Can you derive this one? Can you derive this? Can anybody derive this one? Okay, so if you cannot, so sigma is up and down. So sigma is either up and down, sigma I, or I call it +1 or -1. Okay, so therefore this guy sigma I, sigma j is either +1 or -1. Okay. Okay, let's suppose sigma I, sigma j is equal to +1. So you have only 2 possibilities, -1. Okay. If it is +1, so this is +1. Okay. So therefore, this is cosh minus k plus sinh minus k, which is e to the minus k. Do you agree? If it is -1, you just substitute -1 here. So then this is cosh minus k minus sinh minus k. This is the e to the k. Do you agree? So therefore, if you substitute +1 to here, you get the e to the minus k. And if you substitute -1 into here, you do the k. Okay? So you just rewrite it. So then, so therefore, so this partition function can be written as all possible states, and then product of the neighboring pairs, and then cosh. Am I missing minus k? Seems like I'm missing minus k in lecture note. Or I define wrong way of. Okay, anyway, so let's move on. So minus k, and then, okay, it's a bit sign is different from my lecture note, but let's pretend what I'm doing is okay. So when k is small, so high temperature. High temperature. Is T is greater than Curie temperature. Huh? Okay. Curie temperature. So I think it's okay. Yeah, Curie temperature. So then, so the K is very small. Capital K is very small. T is very big. So therefore, K is very small. K is very. What I'm writing? Sorry. K is very small. So therefore, which means the tansh is also very small. Because in the numerator you have sinh, tansh is sinh over cosh. So therefore, sinh is very small when k is very small. Okay. So therefore, one can just do the expansion in terms of the multiplication of this one. So this is very small number. Okay. So you can just take the multiplication of this guy. So this the product of ij of 1 plus sigma j tansh minus k is approximately given by sum of whatever. Cross first. Okay, sum of, I will explain what the cross means. Tansh of k to the r, sigma 1 and 1, and sigma 2 and 2, sigma 3 and 3, and dot, dot, dot. So what I'm doing here is that so here I'm just doing that so you have a spin, so lattice. Okay, and then sigma I, sigma j is to give you some line here. Okay. And okay, let's go 1 for sigma 1 and sigma 2, and then if you multiply this one, sigma 2, sigma 3. Okay. So therefore, this n1 is the. So if you just write down the like a line like this way. Well, let's go whatever sigma 4. Okay, sigma 5 and so on. So here, what you have is from here you get the tansh k of sigma 1, sigma 2, and from here you just multiply tansh of minus k. Sorry, I need minus k here. Everything minus k. Here minus k. Minus k and minus k, sigma 2, sigma 3. From here, you get the tan minus k, sigma 3, sigma 4, and so on. Okay. So each segment you give your contribution. Okay. And if you multiply them together, you have so you have the contribution like this way. And then, of course, you need to sum over states, all states. At each state, you can have either plus 1 or minus 1 or up and down. Okay, plus 1 or minus 1 spin. So therefore, unless this guy, this exponent is even. Unless this guy even, always, if you sum over all states, it vanishes. Do you understand? So if it is the odd, okay, so if it is odd, the sum over all possibilities sigma 1 is equal to plus minus 1. This is plus 1 minus 1 equal to 0. Okay? But if you have a square, it becomes 2, right? Okay? So therefore, the exponent has to be even here, okay, to get the non-trivial contribution to the partition function. To get the even function, you need this side should be connected to two yellow segments. Okay, here you have a sigma 1 to sigma 2, sigma 1, sigma 2, and so here you have a sigma 2, sigma 3. You just multiply them together. Sigma 2 has a sigma 2 square, right? You get a sigma 2 square. So therefore, this side has a 2 incoming or outgoing, whichever. I don't care about the orientation at this moment. You have a 2 segment connecting to this side. You have the even contribution. So therefore, to get the non-trivial contribution, so you just need to write down the closed path like this way. Okay. So then, at each side you have a 2 segment connect to the side. Then you get sigma 1 square, and you get at the end of the day you get the non-trivial contribution. Okay. So therefore, this partition function can be written. So the high temperature can be written cosh of minus k to the and m is okay. And m is the number of sides in. So here the length is side is number n. The side is the number n. So here, this is the overall factor coming from this side. But however, so the non-trivial contribution is a closed path. And then tan minus k and the length p. So this r, this really r is the length of this path. So you have if you have one segment, you have a one tangent. This segment will give you tangent and so on. So if you count the length of this closed path, you have an exponent here. Okay? And since this 2 really coming from, so 1 plus 1. Okay, 1 plus 1. Really is 1 plus 1. Oh, sorry. I think I should write like this way. Okay. So this is the high temperature behavior of the Ising model. And then moreover, so let's look at the low temperature limit. So what we are doing is, since the compound at the Curie temperature, physics is the most difficult, most interesting. Okay, but if you take the high energy limit, the low energy limit, it's easy to compute partition function. That's why I'm doing that. So let's do the low energy partition function, which is very simple to do that. In low temperature, the spin try to align each other. Okay, since there is no thermodynamic fluctuation due to the since the temperature is very low, so the spin wants to align together. Okay, align together. So therefore, low temperature, the configuration is something like if you take the dual lattice. Okay, so I just do the dual lattice. So this is usual lattice. And dual lattice is something like it's just shift by 1/2. And then you can have like a plus, whatever. Sometimes minus, like this way. So you want to so at the site. So at low temperature, steam wants to align together. So therefore, it's easy to obtain the partition function on low temperature. Maybe I should write down here, but I don't think I can write down. Okay, let's write down here. So the low temperature, so again you have a 2 times e to the n and k. So this is ground state and so the really ground states. Okay. So all possible side is either plus or minus. These two come from all sides are either plus or minus. This is the ground state. But if you have a slight temperature, like a more than at least more than 0 Kelvin, you can have some fluctuation. Okay, and you just some fluctuation would tell us that this one will give you PD e to the minus 2k, and then length of PD. PD means that the so you have thermal fluctuation like this way. If you have thermal fluctuation like this way, so here you can have the chunk of thermal fluctuation here. Okay. Unfortunately, yellow and the green cannot distinguish. I will write down like this. PD means path in dual side. Okay. So you have path in dual side. You have a non-trivial interaction minus plus. Okay. Here minus plus and minus plus. So at this length you can have the thermal fluctuation. Okay. You have a 2 times length. Okay. Because of this Hamiltonian. Because of this Hamiltonian. Okay. Okay, so then if you compare this high temperature, so you can easily see this high temperature and the low temperature is very look-like. I think I made a mistake in sign, I guess. I think I should take the here minus k and plus k. Yeah, I think this is more suitable. Yeah, this is correct. So the lecture note and then here signs are different. I think I will correct the convention later. I think sign mistake I made. So you can already see the similarity, right? Similarity between high temperature and lower temperature. And then this one was the 2 times h minus 2k. Where k prime and k. So you can replace like this way. So I think this should be also plus. Yeah, sorry. It should be plus. If you change, they change a variable, so no good. This is not good. That's why I think I should stick to the lecture convention. But anyway, so you understand. I think. Yeah, actually, I want to have a minus sign here. Actually, minus sign here. Okay, I think some sign maybe I may mistaken some sign, but you understand. So when K is very small, like a high temperature K is very small, but when K prime is very big, you can just have identity, right? You can have identity. So this is called the. This is called. So there is some duality called Kramer's. So this is called Kramer-Swanian duality. Vanilla duality. The Kramer-Swanian duality is the simplest duality in physics, the most important one. All physicists should know about it. So this is the most important phenomenon in physics, and then all physicists should know about it. And this Kramer-Swanian duality capture salient duality of the salient feature of what's called duality in physics. There are lots of instances you encounter duality when you study quantum physics very deeply. Sometimes electromagnetic duality and so on. But Kramer-Swanian duality indeed capture most of the important feature of duality. We will learn later, so-called it exchange order operator to disorder operator and so on as we learn. So therefore, this one is the most important one. So everybody should learn this phenomenon very deeply. And then yeah, so unless you don't understand this one, you cannot claim as a physicist. I mean, this phenomenon is very, very, very important. All physicists should know that. Okay, so let's take a break and then 10 minutes and then, yeah, I will check convention of this P or P minus 1 of a character. Yeah, if you have a question, just tell me. Oh yeah, I think it should be P. It shouldn't be P minus 1. Where did I make mistake? Yeah, it's okay, it's okay. I understand where I made a mistake. It's okay. Oh, I'm relieved. It's not 2x2 matrix, actually 3x3 matrix, sorry. Oh, it's so exhausting. Okay, thank you very much. Are you sure? Yeah, my impression of the Oh, you're right. Thank you very much. Okay. Yeah, Hamilton has a minus sign, so Hamilton has minus j, and you have a Boltzmann weight is minus h over kt, so minus sign will cancel. Okay, thank you very much. Yeah. So, Shandong, did you bring some homework or like graded homework? No. Does anybody? Oh, you already gave it. Okay. And also thanks for grading. So you're really quick.
Yeah,
Yes.
you mentioned that some people do not calculate the TT, they do not calculate all the T and other options.
Oh, okay. I
They
see.
just calculate the
Some of them.
side.
Some.
Yeah.
Then I think you can just like remove some point, like a half or whatever. How much depends. Okay, thank you. Okay, shall we resume? Thanks for so Yan correct me. So here it should be k times sum of sigma I sigma j. So there is no minus sign here because it's Boltzmann weight of minus beta t over h, and h has a minus sign, and this a minus sign cancel, and it becomes j, and this is equal to defined as k. So everything plus. Okay, great. I didn't erase. So plus and minus plus and plus. So I was made a sign mistake everywhere. Okay, and then so I just checked how the S-matrix acts on S whatever how. Strictly speaking, this one is indeed tau R prime and S prime is all primary. That's more precise statement. So I had last time. So I just write down. I think I write down one R prime and S prime, P minus one and so on. But and then this is actually there's some overcounting, as you can easily see. So here you have a 1 sigma epsilon 1 because of symmetry of this one. Okay. So you have to identify some of the primary state if you in these boxes. So therefore, more precisely speaking, you have to sum over 1 sigma epsilon. Okay. So therefore, S matrix of Eisen model is indeed 3 by 3. So one vacuum and then spin and energy, it should be 3 by 3. Sorry, it should be 3 by 3. And I think in future you have to find this S matrix and so on. I think as well. I already forgot what I have the homework I created 3 or 4 years ago. So you have to eventually find this 3 by 3 matrix. So these are corrections. Okay, so let's take a look at the chromatography unitarity more in detail. So here it's a high temperature and low temperature. So what's going to happen when really Curie temperature? How do you see this chromatography unitarity? To see that we just a little bit perturb the perturbed Hamiltonian as follows. So let's consider the following. B is the magnetic field along x-axis. And the sigma z and sigma x are power metrics of each side. So each side you have a power matrix. But since the magnetic field along x-axis, so you just have interaction term in Hamiltonian. This. And then we introduce, so when J is greater than B, so you can ignore this interaction term with magnetic field, but if the high temperature, this is not the case, so let's impose mu A Z, so this is called disorder parameter. Okay, so if you introduce this disorder parameter, so this means that if you have lattice whatever, you can have at the end to the whatever from the end. So this is the whatever minus n plus 1. So this side is minus n to plus 2. I think my convention is this is n. Okay, anyway, let's change it. So here it should be m, and this is n. You just multiply all the sigma x side at the, along this line from the right end to the a, okay? Whichever left end. I mean, it depends on notation. I'm already tired enough to change the notation, so you can just change your notation by yourself. So then, if you have the, why it's called disorder operator, if you have a spin up state, spin up in the all so which means that if this here this line all up, and if you this line if you do all up, then what's going to happen is that if you act this mu a of c x on this state, then what you're going to get is that the B is equal to, oh gosh, okay. So this means that if you act, where's the so if you act mu a x here on this side, actually from here you just it's from here everything swapped to the down state. Okay. So power matrix of sigma x is since off diagonal. Is it the which one? Which one is minus 1 and which one is plus 1? Both are okay, right? Okay, good. So both 1 1. So therefore, if you act the plus 1 state, it becomes spin down, right? Spin down. So therefore, if you act the mu a x on this guy, mu a x of this guy, you just ordered spin becomes disordered, okay, from this part, okay. Blue one was ordered, but some from A, so everything is swapped to therefore it's called disorder operator. Very much. So nice thing is that the once you introduce this disorder operator, one can easily see the following symmetry. The following symmetry Hamiltonian can be written as minus E sum of mu A C mu A prime. Minus J okay, so do you understand? So sigma Ix is indeed can be obtained by just multiplying, since we know that the sigma x square is equal to 1, right? 1, 1, 0, 0. Okay? Sigma x squared is 1, 1, the identity matrix. Sorry, my brain is no longer working. So if you have A and also, okay, let's use some other color. And another multiply A prime, whatever, A prime, mu A prime. So this side, sigma x cancel, like to go to identity, okay? It's just square of sigma x matrix, power matrix, becomes identity. And what's left is only here. That is give you this guy, okay? And then mu A x is just as it is for here, this guy. So therefore, this Hamiltonian, if you compare with this Hamiltonian and this Hamiltonian, you just swap. The role of J and B are swapped. Okay? And then this spin operator is swapped by this other operator. Do you understand? Okay, so therefore here, huh?
Quantum model of dimension, spatial dimension D corresponds to classical model of spatial dimension D plus 1. So also here, if you consider two horizontal lines at different, I think it's more like a one-dimensional.
Why dimension matters? I don't see that.
You consider two-dimensional quantum Ising model, and the critical exponents are different from the classical Ising. And thus, everything is
Yeah, of course, critical exponent depends on the dimension. That's for sure. But it's one-dimensional. Why? Why do you think one-dimensional? I don't get your point.
A and A prime located at, for example, vertical, then they will not constants.
I see. Good point. I see. So A and A prime are something like this way. Good. That's good point. You mean like this way, right? I think you're right.
So if you do the pass into a formalism, then you can see the one-dimensional quantum Ising model correspond to two-dimensional classical Ising model. So
Okay. Good point. I didn't pay attention to this difference. This is a good question. Okay, so at this moment, let's pretend a one dimension, then this duality makes sense. But I don't know. But from now on, we're going to talk about 2D CFT, two-dimensional CFT. Okay, how to think about it? Why is it? Okay, so let's pretend we at this similarities hold only t equals 1. Anyway, so yeah, thanks for the question. This is a good question actually indeed. So low temperature. So you can neglect low temperature. So you can neglect this one, this term, and then what you get is the sigma z exception 0, because I mean low temperature you want to spin wants to align each other. Therefore, expression value is this guy is 0. On the other hand, non-zero, but for this other operator, in 0. On the other hand, for high temperature, so high temperature, this Hamiltonian dominates, then this term dominates than this guy. Therefore, you can have this other operator is non-trivial. On the other hand, the other operator, exponential other operator is the this is high temperature. High temperature, so the other operator has non-zero expectation value. On the other hand, you can just have the 0 exponential value of a spin operator. Okay, to see what's going to really happen in the Curie temperature, we need to identify the primary state with the so high temperature and low temperature. So Kramers one-year duality sub sigma and the mu. These are the operator. And in fact, so since they're swapped by Kramers one-year duality, it should have the same conformal dimension. It should have same conformal dimension. Moreover, it's called mutually non-local. So sigma mutually non-local. So I will explain what it means by mutually non-local. So mutually non-local means that if you have operator mu here, it's a mu operator here, and then you try to bring the sigma, sigma from here, whatever, sigma operator from whatever, okay, let's go 0, 0, and C bar, and they just rotate 2 pi. Then indeed you get the sign. This is called mutually non-local. Goes to sigma e to 2 pi I. C e0 minus 2 pi I. Z bar and mu and 0. And this is indeed get the signature. And in fact, so this means that this mu creates a branch cut here. And once you rotate branch cut, once you rotate sigma around the mu, you get this relative sign in front of. So this means the mutually non-local. Mutually non-local. So you cannot define the sigma mu at the simultaneously. So locally. So there's a global effect you encounter once you rotate the 2 pi. And in fact, so this indeed is the give you the, if you look at the OPE of this operator, indeed, this is indeed equal to Z quarter and Z 1/2 psi 0. Actually, it's a bit ad hoc, but you understand. Okay, you get some reason why you can have fermion. So if you have so if you take the OPE, you get the fermion. So due to this OPE fermionic OPE, this minus sign will appear once you move around. So you cannot define locally sigma and mu. There's always global effect due to this fermion. And since we know the minimal model, it's a bit ad hoc derivation, but it's if you identify the primary field in minimal model of p equals 3 with the operating Ising model in the following way, that everything makes compensing by 2 1 Z and then by 1 1 okay. And the psi bar is the psi 1 1, so this is the primary the Z bar, sorry, and it becomes tilde, it's not tilde. 2 1 Z bar, and then psi bar is indeed equal to energy of density operator, which is 2 1 and 3 plus pi 1 2 2 1 2 1 Z bar, and we can just have spin or order operator. This order operator can be identified as pi 1 2 3 plus phi 1 2 in minimal model. Yeah, so right hand side, this one is really minimal model p equals 3. The phi h phi rs is the primary field in minimal model. And you can check the conformal dimension. So we know that the phi 2 1 is 1/2, and this is the identity operator 0. This is 1/2, 1/2. So it's the same as the conformal dimension of the fermion. And also here you have 1/2, 1/2, and multiplying together is the 1. Oh, sorry. So what I'm doing, what I'm saying, sorry. I completely told you wrong thing. Sorry. Am I saying what I'm saying? What I'm saying here, I would lose my my brain's not working. Sorry. So this is component dimension 1/2, 0, 0, 1/2, and then here 1/2, 1/2, and 16 and 16. Sorry. So this is the component dimension, and then so this is consistent with component dimension of the fermions. And once you identified the this one, you can just easily see the fusion rule is 1 plus epsilon. So this can be read off from fusion rule of primary operator. So moreover, associativity of the OPE can be derived. So you can just have psi of C sigma W bar is indeed. You can just use the OPE of this primary field, which already given in the so you can derive this kind of OPE, and also if you do the model expansion of fermions, one can identify that the psi of C of sigma 0 is indeed Z minus R minus 1/2 and R, and then sigma 0. And if you compare with both, so one can just show that the B0. So 0 mode acts on sigma 0 is indeed you can just show that. Okay. Okay, any questions so far? It's a bit ad hoc, but once you identify the operator like this way, one can just have a consistent OP relation. And moreover, so since we have the character, vacuum character, so 1 and the sigma and epsilon, epsilon and sigma will create the eraser module, and then you can read off sigma 0. So if you use the formula given below, one can just check is equal to trace of an S sector 1 plus minus 1 to the F Q to the not minus. So the character is already I have written down, and you just put the P equals 3. And you can show that the character, vacuum character, is indeed the product of these two zeta function, and the chi 1/2 is equal to 1/2, and zeta 3 eta minus 4 over eta. This can be just set the P equals 3, the formula I have written down in the first class of this today's lecture, Q to the L0 minus C over 24. And also you can have so this is character for Eisenmodel. Oh, sorry, this is character of Eisenmodel. And then since you can easily see that so here the Eisenmodel clearly can describe free Fermat, and here is expression by free Fermat. Expression by free Fermat. Okay, so and then I forgot to mention. So where does the square root come from? 2 lectures ago, I couldn't explain what the square root 2 is. So as you recall, torus partition function Ramon and okay, periodic. Am I correct? I think I'm correct. Sorry, I think. Periodic, anti-periodic. Sorry, that is correct. Periodic, anti-periodic is indeed equal to trace of Ramon to Q to the L0 minus C over 24. And then last time I couldn't explain why this is 2. And then product of 1 plus Q to the N is greater than or positive integer. Positive integer. I think I didn't explain this group two lectures ago. This 2 is indeed coming from, so you have to take, so this is indeed equal to square root theta 2. There, right? As far as I remember. I didn't print out the lecture notes, so let me take a look at it. Yeah. Where did I keep the definition of this character? So 2 lectures ago, I couldn't explain this curve 2. Yeah, good. I think what I have written is correct. Yeah, except Q to the. Here you have a Q to the. This 2 I didn't explain. In fact, this 2 is indeed, so this is a homomorphic sector, and if you consider anti-hom sector, so you need to have Q to the L0 minus C over 24, Q bar, L0 bar minus C over 24, then you should get theta 2 over 8. Okay? Theta 2 over 8. And this is indeed equal to QQ bar 1 over 24 times 2 times 1 plus Q n, and then 1 plus Q bar n is supposed to be integer. Then this 2 is indeed coming from the vacuum states and the Fermat zero mode. I call it B0, right? Mirror 0. Fermat zero mode. B0. So both have the same energy. L0 is equal to 0. L0 acts on is 0, and also L0 acts on B0 acts is 0. Okay. So you have a 2. So Q to the 0. Okay. So you have to sum over all Ramond states. Since you have the problem 0 mode, there's some degeneracy. Okay? So therefore, you should get 2, and this curve 2 is really actually coming from anti-holomorphic sectors. That's what's really happening. Yeah. Anyway, so here. So, okay, okay, then I don't need the square 2, sorry. I don't need the 1 over square 2. It should be this one, sorry. Am I correct? I think, I hope I'm correct. Maybe not. Yeah, I think I need the square root 2. So then this is indeed equal to square root 2 of this. Okay. Okay. Yes. So here you already have the formula for. Here you just. So this formula can be obtained by substituting characters. So I have written that down like this one, right? This one is equal to 1 over eta and the theta minus theta. That's already. I'm not going to write down some subscript. And if you substitute the proper value p equal to 3 and the rs, this is 1, 1, and this is 2, 1, and 1, 2, you can obtain this one. But this Jacobi set of function you already encountered by Torres partition function, and then of free Fermat, you can just write down everything in terms of free Fermat. And in fact, so diagonal Z diagonal Ising model and P equals 3 is chi 0 bar plus chi 1 half plus chi 16 chi bar 16, and this is equal to Z frame, free Fermat. Okay, so this is not a coincidence because since the central charge of the minimum Ising model is equal to 1/2, and also free Fermat central charge is equal to 1/2. So it's equal to 1/2. So therefore, you can have both the spectrum of a character of the Ising model and free Fermat are identical. Okay, so this is the p equal to 3 case. Let me move on to the other cases. So what happened? P prime is equal to 2 and the P is equal to 5. So this is called linear model. So this is called linear model. So here, so M to 5, central charge is easily to computed. C is equal to minus 22 over 5. Where was it? I have written down formula for central charge. Unfortunately, oh yeah. So 1 minus 6 p minus p prime square, and then PP prime. And if you plug that one into here, you can just check that the P minus P prime is equal to 3. 3 square is equal to 9. 9 over 10 minus 1. And in fact, if you compute it, 22.5 over 1. Okay. So this has negative central charge, which is already the sign of the non-unitariness, and also H12 is the negative compound dimension. Negative compound dimension. So it has non-unit. So this will create a sign that they are non-unitary. And in fact, so here, so Lee and Yang noticed that if you consider the Ising model with the magnetic field sigma I, sigma j, minus b, whatever, sigma I. If you look at the partition function of this Ising model, it has a singularity when b is imaginary, purely imaginary. So you just treat this partition function, so you can just consider sigma of e to the minus beta h, and then all states. The partition function should be written in terms of the j and b. In terms of j and b, and Lee and Yang found that the EJB has singularity at some value when B is purely imaginary. Is purely imaginary point. Yeah. Sorry, 0, 0. Sorry, not singularity 0. Yeah. 0 at the purely imaginary, because purely imaginary. And in fact, this 0, this is in fact indicates that there is some sharp or new. Like a non-unitary model that describes this purely imaginary part. And in fact, this can be proposed by Fisher, that if you consider Lagrange model, like a two-dimensional Lagrange model, which is some scalar field and square plus I, E minus C, and sigma plus IG sigma cube. And this two-dimensional Lagrange model can be described by at the Liam model at IR. So this is the proposal by Fisher, and then non-unitariness coming from really this I. So imaginary part. Non-unitary. So this is one comment about how the non-unitary model appear in the theoretically, but this does not describe, since the B is purely imaginary, so you can just not have the physical as a physical model. Okay. And a brief comment on other models. So MP is equal to 4 is tri-critical Ising model. So for this indeed describes the Hamiltonian something like this way. So T sigma is spin variable, and T is equal to vacancy variable, okay, which takes the value of the 0 and 1, and then Hamiltonian can be written as the spin and the vacancy and the mu. So this is IJ, and at the critical temperature, again it becomes conformal field theory, and in fact, so this conformal field theory describes a minimum model of p equal to 4. This is I equal to 1 to n, I equal to 1 to n. Yeah. Yeah. So here, sigma, of course, sigma I takes the value of plus minus 1. Yes, sigma. And the Ti is the vacancy variable, so 0 or 1. So it can be 0 or 1. So this variable specifies whether the side is empty or not. So this side is empty or not. It's a take or not. And then mu control the density of vacancies. So this is chemical potential. So therefore, you can just have so you can have a lattice like this way. But however, some side can be empty. Some side can be empty when T is equal to 0. So this is the Hamiltonian for the strike-critical Ising model. And then if you consider the critical point, which is specified B and T, critical point, you can just describe by using m equal to minimum model p equal to 4. Okay. Okay, and also one can just consider p equal to 5 case. P equal to 5 case is a bit more interesting, and p equal to 5 is called 3-state Potts model. So the Hamiltonian. So 3-state Potts model is that so it's no longer the spin variable is no longer plus minus 1. You can have yeah, I mean this is IJ, and IJ. Now sigma takes a value is the omega j. J is equal to 1 to 3, where omega is a third root of unity, 3 pi I over 3. Okay. So instead of plus minus 1, you can have the third root of unity. So this is an interaction. So this is complex conjugate. Bar is complex conjugate, and so on. Yep. And you can see that the you can just compare with the conformal dimension and so on of primary and so on. One can identify this. I mean, spin variable is 1 over 15, and the conformal dimension of energy density operator to 5. And there's the other So there's another, conformal dimension, a primary operator. Okay, I don't understand this part. Moreover, So interestingly, this admits non-diagonal modular invariant partition function. This is the first instance you can see the modular invariant partition function, which is non-diagonal. So we can show that the Z 3 box is equal to R is equal to 1, 2 chi R1 plus chi R5 squared plus 2 chi R3 squared. So this is the partition function of the 3-pot states. But here, as you can easily see, so this will give you the non-diagonal part. Chi R1, chi R5, bar, chi R1, bar, chi R5, plus chi R5 squared. So especially, this part is really the instance of non-diagonal part. So you can have a pairing between different conformal dimensions. So this is the first instance of non-diagonal partition function, and then I think I should mention one thing about this three-state box model. I think I should mention one thing. So it has, so H51 is indeed equal to 3. And that corresponds to some primary operator called W of C. It has a spin 3 state, a spin 3 operator. And in fact, so this T, so we know T of C will give you a Virasoro algebra. Ln is equal to n minus m ln plus m plus c over 12 n squared minus 1 delta n. Okay. In fact, so this W, so T and W, so we know that here conformal dimension of T is 2. And the conformal dimension of W is 3. And in fact, T on W of T is called W higher rank generalization of Virasoro algebra, which is called W algebra. In fact, so you can just take the W of Z, W written sum of Wn, Z minus n minus 3. You can have this kind of model expansion. So then you have Ln, Lm, and dot dot Ln and Wn, and dot dot and Wn. Wn, Wm is equal to dot dot. It's complicated. It's super complicated. But this is some higher rank. So Virasoro algebra is kind of related to SU2. But this algebra is related to SU3 and so on. And you can have higher rank version of W algebra. So this is the, even though it's a complicated, so it's more interesting. And some people knows about, hear about the so-called AGT conjugation, some relation between two-dimensional conformal field theory and some four-dimensional supersymmetric field theory. And this W algebra plays very, very important role. Okay, so these are the other model. Okay, I think I spent enough time on this one. Last 15 minutes, let's talk about conformal bootstrap. And let's stop it. Okay, let's talk about conformal construct. So we know that the two-point function primary phi1 of z, phi2 of 0 can be written as g to h c1 2. Okay, so that's we know z bar. And then h is equal to h1 and h2. Has to be h1 and h2. And you can always scale the primary so that the primary scale, you can just have a 1 in the numerator. On the other hand, you can have phi1, phi2, phi3 is given by 1, 2, 3, v1, 2, h1 plus h2 minus h3 and secret. Then this guy cannot be scaled to 1. And it's always, this numerator always depends on the 2D CFT. Depends on 2D CFT. Given a 2D CFT, and so 2D CFT has a bunch of primaries, and you pick 3 primary out of this kind of primary. Then you just try to compute 3-point function. And here, the denominator is fixed by conformal symmetry. Okay? You already showed that. But this guy, really, it's really difficult to determine this C1, 2, 3. Depends on 2D CFT, and it's very difficult. Rational conformal filter you can determine. Minimal model you can determine C1, 2, 3. And however, it's not so easy. So in general, this is lots of open problem to determine this numerator of the 3-point function. And then, so as I have written down, sorry, I just came back from Shenzhen last night, midnight, so I'm already exhausted. It can be written as something like so coefficient C1, 2, P, and then K, and then K bar, and then C, H1 plus H2 minus HP plus K. I'm only talk about the homomorphic part, and K bar, and then let's so you can always have an OP like this way, P. So given two primary state, if you take OPE, you can have the conformal family, sum of a conformal family of primary states P, okay, sum over P. And this coefficient can be always determined, so the K and the K bar is of course the how many, so you just act the lots of Virasoro generator on the primary state, so whatever. So as you recall, L minus 1 of phi of P of Z or 0 is we call it phi minus 1 of 0. Okay, so this is how you define and so on. So this is descendant operator. You can and the C1P 2P okay. I think I should call P like this. KK bar can be determined. Okay, it's if you look at the holomorphic part, it's only this one. So this can be determined by C1 to P. P means really here, 3-point function. So coefficient of the here for descendant can be obtained from the primary 3-point function, the coefficient of the 3-point function of the primary field by solving BPC equation. So recall that the if you have the primary phi minus minus 1 z phi z1 and so on can be written as L minus 1 acts on phi t phi 1 t1 and dot dot dot, and this L minus 1 can be written in differential operator. Okay, so this can be written in a differential operator. So once you have a correlation function of primary, one can solve correlation function for descendant, including descendant. So by solving BPC equation, one can always fix the coefficient for descendant. But to fix this one, you have to know about the primary one. But this one is a lot of open problems, and one approach is so-called conformal bootstrap. Okay, since I don't have so much time, so far we talk about the 3-point function. So one can consider 4-point function. 4-point function. So this one, can be computed either this way. 1, 2, 3, 4, P. Oh, sorry. 1, 2, 3, 4. Or you can just have P, C. Let's see. 1, 3, P, C, 2, 4, P. Maybe I should go, let's go Q in that case. Like this. So here, so this diagram in fact means that you just take the fusion of phi 1 and phi 2 and you get a bunch of conformal descendant of primary field P or Q. Okay. If you take a fusion on 1, 2, you get the OPE. So another operator will appear, which is usually primary or descendant of another primary field P. So this internal channel P really depends on really represent this guy, phi P of descendant. And also you can do the same thing. So 3, 4, and fuse them together, and you get another operator. And if they matches, you can just sum them over. And you can sum them over. And since you have a 3-point function here, you have the coefficient here for this guy. And also, if you fuse them together, you get another OP coefficient here. Okay. But you can have the different decomposition like this way. And these guys are called conformal block. And this only, the important point depends on algebra, bilateral algebra. Sometimes later we will see if you go to Western model, this becomes affine Lie algebra, Katsumaki Lie algebra. Some generalization bilateral algebra. Sometimes it becomes W algebra, and so on. So it only depends on symmetry. It doesn't depend on the two-dimensional conformal filtering. So all minimum model has a symmetry as a bilateral algebra. So therefore, they all have the same conformal block if they have the same conformal dimension. And this can be written as the function, some rational function. So rational function of the conformal dimension H1, H2, H3, H4, and HP in HP. And the central charge. It's not depends on central charge. Yeah, it depends on and central charge. So it only depends on the conformal dimension and the central charge and the algebra. But however, this C really depends on the for instance, Lagrangian action of the two-dimensional conformal filtering. But if you compare, so you can just have a function of the conformal dimensional central charge. One can solve this equality to determine this OP coefficient C, to determine a 1 by 1. That is called a conformal bootstrap. So by comparing these two diagrams and determine C is called conformal bootstrap. So bootstrap means you can just bootstrap. Bootstrap is here. It's a tedious, which means it's tedious. But if you compare 1 by 1, one can determine C completely. That's what it means. Okay, so that's especially for minimum model, one can determine this coefficient C exactly. Okay, so this is the idea of conformal bootstrap. If you're interested, you can take a look at more. Okay, so let's stop here, and the next time we will move on to renormalization group 4, and the most important thing, so Zamolodchikov C theorem. Okay, that's what we're going to talk about. Yeah, any questions? Okay, then let's stop here.
Why don't we consider descendants here? Why do we have descendants here? If we want to use this one.
So you can have descendant here, but as I mentioned, descendant, this one can be determined C1 CP. So everything will package into here.
So it will be a function of the...
Yeah, in some sense, yes. So what is the problem of the TOP? Okay, you have to definitely include regular.
I just use my 我回去看我当然看到了。是啊，但是它上面写的这个这是这不是人民币，这个呀是日元，这个也是。
So I think I should stop it.
我就说他怎么